So, and good afternoon. We continue from the video refer to mass integration slide. Here we do the first thing to do the for this slide. I'm referring to book by Handbook of Process Integration. It's ELIP, page chapter 10, page 368. Books and paper is available. So these are in the video based on this chapter 10, water visualizes for water management and minimization. Here's how many steps? 5 steps overall. So step number 3 is the setting the minimum utility target. That one, there are a few step methods. We have limiting composite curve, LCC, and water cascade analysis, WCA using the table, and sourcing composite curve. So from all the method, only one method that using a table, which is easier. So once we identify the minimum utility target, either the fresh water or the wastewater, we need to design the network, water network. So for water recovery network, there are 3 important heuristics. First heuristic, 3 heuristic. The first one is do not feed water source above the pitch, including fresh water to sink below the pitch and vice versa. Meaning, once you identify the pinch point, this okay, this is the example of pinch point. If you use sink source event, so another definition, another synonym for sink is demand. The demand. Okay. So the meaning for the first heuristic is do not feed water source above the pitch to the sink below. So water source for this graph, the water source above the pin is considered as source 2 and source 3. And in order to design the water network trophy, do not feed this water to the sink below the pitch point. So meaning these two source goes to sink one and sink two. It has to be noted that in order to achieve fresh water and wastewater water target, sorry, yeah. It is necessary to observe the pinch division. The water sources above the pinch, including fresh water, may not be fit below the pinch and may not mix with the sources that are below the pinch concentration or vice versa. So meaning anything above the pinch must not be fit below the pinch, including the water source. What is the number one or heuristic number one? Second heuristic is start the sourcing matching process with the sink at the lowest contaminant concentration. So after all the sink and source have been separated according to the pH division, above and below pH concentration, how do you know? Either you use water cascade analysis to define which um, page 264, right? So if you use water cascade analysis, this is a water cascade table. So the pinch come in this concentration of protein. Then we go in depth how to use the water cascade analysis in the case study. For anything below the pinch, this is the line, this is above the pinch. So for the rule number two, all the single source in wait, all the same in source in the water utilization network will be mixed according to their contaminant constraint. This means that the sink with the lowest contaminant concentration is first matched with the source with the lowest contaminant concentration. The quantity of water from the contaminated source that will be required to provide the contamination load located with the sink is determined by the maximum contamination delta M for each sink. Contamination load for elevation I can be calculated as follows. To calculate for the load for the contamination, we refer to this equation 10.3, page 269. Delta M over delta C times delta S. That is rule number two. So rule number two states that the source is matching process with the sink at the lowest contaminant concentration. So because when you either you use LCC, sink source diagram, the first thing you need to do is uh, to sort it, to sort the sink and source in ascending order based on the contribution, contribution right. Contribution right. If you can ignore it, you this is the HLYT paper in 2003, before the page 4,235. This is the data. Yeah. Mm, So this is the example of the termination mode. So like I said, the scene we have the source is based on uh, process flow diagram. So this is what I told you. Um, Inlet, the concentration, sorry, we sorted in ascending order from the lowest to the highest. And we rename them the lowest with the scene 1 until 6 and similar to the source. Third rule or third rule is to make the available resource one or the other and add fresh water as required to sink according to heuristic one until all the sink have been satisfied in terms of both quality and quantity. And we will have done 2005. 2005. Because this book is fully based on the program paper. Sorry, it's the paper. Need to check. I found it earlier than check in the elite. So what does this rule 3 means is for SK1, for example, if it's require 50 ton per annum. So the fresh water incoming for the sink one and source one should be matched that is it, requirement of the sink one. Later we have the example. Alright, so we go to book. This book is Handbook of Process Integration. Page 369. Okay. So Poly and Poly 2000, okay, we have people in reality. Propose a design principle regarding the systematic tracing source and stream with each other and where necessary with fresh water to produce a stream. We just meet the target of the individual sink in terms of both quantity and quality. So if you refer to this paper, interesting how they determine the usage and how they design the Uh, Three design proposed, each have its own advantage and disadvantage. The result take one of the following four. If this quantity is equal to the required value, then no fresh water needs to be supplied. But if it is less than the C, then some fresh water is required. This is the rule of thumb. If the quantity required from the source exceed the sink, then part of the sink contaminant lot should be satisfied using the source having a higher contaminant concentration. So constraint for network design between source I and sink J are given as policies of different people. This is 2002, finally, made calculated the flow rate and the concentration of the sink. But what I like to show you is, okay, this is the example. This is still under um, step number 4. Okay. Water network design slash traffic. Okay, this paper, this 10.11 is basically paper by the consultant. So all the water sink are aligned horizontally at the top. This is the sink. Or if you refer to the actual paper, it's using a demand. It's the same, sink and demand. While all water sources are lined up vertically on the left side, here, this is the water source. Both are arranged according to increasing contaminant concentration. So figure 1011 show one possible network generated by the source sink mapping. It is emphasized that this is only one of many possible solutions that can achieve the target. Yeah, of course, that is correct. Mainly based on how much fresh water that certain company can afford to be within their costing. The designer can influence the solution by imposing other concerns such as forbidden of force connection for safety or economic reason. However, this additional constraint may sometimes result in water penalty. Water penalty means you require more fresh water instead of how much is this? 75. So in order to make it less complicated, this is quite complicated network. So to reduce the complication, we need to add some water penalty, meaning to increase the fresh water. See? Okay. Alright. So you can download from the ELIP. This is the demand and source. You see it's sort in ascending order. Okay. This is so the figure 8 here refer to figure 8 here refer to the sourcing mapping like that in 10.11 book of process information. You see the structure shown in figure 8 consume the minimum quantity of fresh water, only 770 ton per hour fresh water, but involve a lot of control mixing upstream This is undeniable in terms of safety and probability and capital cost. You see, source one will need to go to first seek or demand one. Some of it will goes 20 will goes here to meet the requirement of demand one, which require how much? See here, 50. Absolutely. The first one require 50 ton power. So some of it is coming from fish metal, some of it is from source one. So the source one has 50 ton per hour. So 20 goes to the first demand, the second one goes to the second demand, second sink. So second sink 30, but the second demand require 100 ton per hour. So the remaining goes coming from fresh butter and from the source. You see the complication, many division of line here. So by increasing the freshwater flow slightly, need to impose a water penalty, it is often possible to reduce the complexity. So by adding 10 ton per hour of freshwater, we can reduce the complexity of the water network. This is done by developing a spreadsheet representation of the network involving how adjustment to the freshwater flow rate in the distribution of the flow affect the demand made from the well source and the continuation level of the new demand. So by increasing water flow from 70 figure 8 to 80 figure 9, achieve a significant reduction in network complexity. If the cost permit by increasing up to 100 ton per hour, it is a very simple network. You see, fresh butter goes directly to the first seed or first demand, and the second source one goes straight to the demand number two or sink number two with addition uh, from the fresh water. Only one split here, but this is from source 280 goes here, then the remaining is the waste. This is straight to the okay. Um, all right. Return to handbook of process integration. Another method here by El Halwagi. This is based on the sourcing allocation composite curve. The sourcing allocation composite curve can be used to show the water network allocation or design between the source and sink. So the sourcing composite curve refer to the third method under step number 3, the sourcing composite curve. Yeah. Uh, in constructing a sourcing allocation composite curve, El Hierarchy proposed the step where the authors assume freshwater has zero baseline. Satisfy a sink using the water sources. If the sink baseline is met but not the flow rate, add fresh water. For example, in figure 10-12, this is the figure. Sink 1 or SK1, this is the SK1. We can be specified by part of the source 1, or FSR1, and also by freshwater flow rate of FWSQ1. So FWSQ1 is not here, but it's already here. The, because when you do a sourcing like composite curve, you need to make this show. You need to you need to draw it like this first. So the source and the sink, this is the first step. Where you get the source from the table. How do you know this is source Manchester? You sort it in ascending order. You draw this first, then you shift the source below the sink, like this. So the gap here refer to the fresh water, which is the FWSP1. This is the wastewater. Minimum wastewater. This is a minimum wastewater. Okay. And sink 2, SK2, this line, is satisfied by the remainder of source 1 here, source 1, and what else? And also, sorry, a part of source 2 here, remainder of source 1, part of source 2, and fresh water FWSK2 is a gap here. So this is the fresh water is sink 2. The procedure is repeated until all sinks have been satisfied by the available source and fresh water. The method location for each sink is shown on the y-axis in graph. The vertical location is presented by on the x-axis. The sourcing allocation uh, the sourcing allocation method by MLYG it all uses a concept similar to poly and poly 1000. To propose that the cleanest source be reused first to satisfy the cleanest sink, which is true if you remember this method. The first source goes to the first sink. The cleanest source you reuse first to satisfy the cleanest sink. So the first sink is the cleanest. What else? So if the quality of the sink has not yet been met, but the correct quantity has, fresh water is added. The same illustration was shown by Kazanzi and Elwagi 2005. For fresh water, but this is the Elwagi 2005 source signal location using composite curve. So for fresh water with non-zero base load and superior to other stimulation of figure 10.13. The cleanest to cleanest matching rule used by Poly and Poly Elwagi and Kazanzi was later found by Wat Alwi and Manat. This is a paper in 2008. 2008, yeah. If you refer to this paper, it's published in 2009. To only cater for the fluoride deficit case. Example, the case where the base load of zinc is satisfied but not its fluoride as shown in figure 10.14a. Is uh, although it satisfied the demand, see, the flow rate is not satisfied for the SK1. This is the flow rate deficit. Another case is the there is another important case which is the best lot exit case, where the source meet only the flow rate of the sink but not the best lot figure. This is the two deficit that we found out by one Almi and Mana in 2009, which they proposed another method. The collective water source below and between pinch region have to basically have the same flow investment as the collective sink. So that not that using the cleanest source does not meet the best lot of the sink, result in an excess best lot of source and equally an unsatisfied flow rate for subsequent sink. Hence, what Alvimana have introduced another rule for the best lot of sink, which is to satisfy the best lot and flow rate of sink using the cleanest as well as the objective source for the clean region and making sure the pinch point identified are satisfied. So how to do it? They author introduce a new method that growth allocation diagram, which state the source signification correlate with a method mapping diagram diagram for easy visualization in figure 10 and 15. So the 1015 is kept based on the article in 2005. Though in this book it's 2008. All right, let's see. Oh, we are sharing. Okay. Oh, yes. Um, go to paper bundle earlier. So this paper, we introduce network allocation diagram. The first step is to draw the source and demand conversion curve, SDCC. This is it. One SDCC of nitrogen. So the nitrogen case study with two with two environmental. If we so this paper is about so if you method decide this is a gas cascade analysis. It's similar uh, some differences of course because water is not like a gas. The way it behaves is different. So that one is based on the because in this paper by who it's a few example of interpreted. This example number one, nitrogen integration. So the nitrogen integration is two gassing and two gases identified from the process flow diagram. It's for the stream of drying, which is 5.5. 14, which is 3. The member related, which is 3 as well. And drying, 5.5. So guessing guesses. So it's similar. So for the SDCC is what refer to the sync. That's only should refer to the source. Okay, we have demand one, demand two. Okay. Sync one and sync two. So the source and demand for the curve is DCC. Okay, the demand here refer to the C. Not sure why they have this total. Okay, let's sync as demand. So the source and sync composite curve, source and demand composite curve, and LLD is used to match the allocated the best load employed of the source and demand. So the y-axis of the SDCC represent the cumulative mass load. Yeah. Cumulative mass load. And what else? So 8.5. In order to satisfy a demand, cleaner source is added to the cleanest demand. Is sending the solution to meet the mass load and product requirement. To obtain the target impingement from the source and demand for the curve, the source line is shifted to the right first. So this is the source, then it shift. Understand that? This is the source, then you shift it, and then it meet the point of the demand here, which is the pinch. Yeah. So the step two is construct the source demand allocation curve. So the source demand allocation curve is in figure two. Okay, figure two is the figure two. In which they identify the fresh water, fresh gas target here. In this case, because it's a gas, about 4.25 kilogram. And there's what is it? A gap for the source line before it goes to the source two. So that gap is the fresh water as well. So fresh gas. So 1.38. This one. Once you shift it, there's a gap. So this gap is the fresh gas. This example is based on case. So once you get the allocation curve, source and sink or source and demand allocation curve, then the network allocation diagram. Okay. Network allocation diagram is drawn from the source and demand allocation curve, AC. Yes. Referring to figure 3, you can download this paper. Figure 3, the mapping of the source 1 this is the source 1 and source 2. This is the gap between the source 1 and source 2, which is the fresh gas. And the fresh gas FG to demand 1 and demand 2 are graphically shown by boxes drawn below the x-axis. Note that the width of the boxes represent the stream flow rate of the individual source and demand line. The NAD is completed by drawing arrow to match the fresh gas and other gases to the demand. So we refer to this table. This is the FG refer to the allocation curve. So we have two fresh gas, 1.25 and 1.38. So demand 1, demand 2. This is the waste gas. Waste gas is from the last point of the demand 2 until the end of the source 2. This is the waste gas. Then is for the fresh gas, where we have the S1. This is based on this graph. Because we want to create a network. It's not just to to identify the limiting, the minimum wastewater, minimum freshwater, or minimum gas, fresh gas, minimum waste gas. This is to create the new network. But based on poly and poly, it's not that straightforward. Sometimes we need to do some penalty. Okay. So the fresh gases, this is the S1 reminder of the S1, still S1 here, then S2. So the fresh gas goes to the what? This is the fresh gas. So for the S1, it's 1.25. And 1.62. Let me calculate this. 1.25 plus 1.63 plus. Yeah. So if you total up, this is actually 5.5, which is similar to the Sing 1 kg per second. 5.5. So S2 is the waste case. Okay. So this one, it doesn't give an actual value from the graph. How can we calculate this? Possible. But some of the source, so the sink source one of it is goes to the S1, then some of it is goes to the S1, the remainder of the S1, and then to the S1, which is the West gas. So from here, was the okay, let me read this first. The NAD is completed by drawing arrow to match the fresh gas and other gas source to the demand according to their flow rate, matching stream matching in the source distribution. And ultimately, the receiving gas can be network design. So step 4 is perform the network evolution. Okay. Two rules can be applied to evolve the network design. First, uh, in order to ensure the minimum water rate and avoid water penalty, use the SDAC source demand allocation curve to shift, cut, and locate resources to satisfy the best load. And flow rate requirement for each demand individually in a given each region. With secondly, to ensure the maximum number of stream and reduce network complexity, use the SDAC to shift, cut, and allocate source to satisfy demand quantity and exclude the quality. And figure 4, this is the figure 4 shows the maximum gas recovery network design for the nitrogen recovery case study, which is generated using the SDSC and NAD. If you refer to uh, you by food, six. Okay. Paper by four and mana ni? So this paper, it doesn't explain in detail how they create the water network or the gas network. Once they identify the limiting. So in order to learn about how to react the water network, we need to refer to one of it is this paper by Arman Alvi in 2009. Alright, yes. Okay, step number 5. So, step number 5. Okay. Okay. So the step 5, the last step. If most author resort to complex mathematical modeling in order to calculate the network cost, going into detail piping routing, geographical constraint, associated fixed and variable costs, preliminary economic calculation. The payback period is widely used as a criterion to assess the feasibility of a proposed network solution. The payback period is calculated using the equation 10.7, system 10.7. The net capital investment is the investment needed for pipe rewriting pumping, storage tank for intermittent process and control system. The net annual saving is the amount of saving result from the freshwater reduction. So the idea is we want to reduce as low as possible the freshwater. So that's why any increment of the freshwater, they call it water penalty. So how much is the capital investment over the annual saving from the fresh water of the or the fresh gas? It is the big result. Okay, this is example. Let's see. Example. Ah, which book is this? It's here chapter 10, page 246. So 10.5, water pinch technology. The first problem, problem 8. A certain process contains several water processing calculation as one example 10.22. A, create the limiting conversion curve, LCC, by plotting the contaminant concentration, C against contamination dot A. Calculate the minimum water flow rate for maximum relief. Alright. So answer to A, this is the equation. You see here. Is it sort it in ascending order. The individual associate A, the individual limiting will profile a graph in figure 10.29. This is 10.29. Figure 10.30 shows the result when these water profile are combined. So this is the LCC. LCC, we have a sink source diagram. The one is different. This is a limiting composite curve. Another one is the cascade analysis. By the previous example is based on the sink source um, sink source curve, composite curve. So first one is the first operation from 0 to 2. Sorry, from 0 to 2 the particular flow rate, and starting from 0 ppm to 100 ppm. Second one, 2 to 7 is a cumulative. So to and at 2, so start from here from 2 to 7 for the second operation. So from 50 to 100, and then for this version 3, it's from 50 to 800. Version 4 is 400 to 800. So this is the limiting water profile. So combining the limiting water profile for problem 50, we have is 10 to T. You see how they combine it here. Wait, erase this. Oh, cannot erase. Okay. You cannot erase. So if you if it's then it should be login. Yeah, Jiri. This is based on sustainability in the process industry, regulation and optimization. Okay, so this is the second group. Sustainability. This is by Jerry Clemes. Chapter 10.5. This one. So it's look like this. You see now the road, the ball, black line. Once you have this line, you can also click and book of process delivery. Similar. That one is good one. Similar is page. Yeah, page 363. Limiting composite curve. One is mid 1990, one is based on one is mid. It's similar how they identify the page. So once you have this ball line, what you need to do is from zero, you create a tangent to this lowest curve. So the tangent is the pinch for this process, pinch point. The second question is what is the second? Calculate the minimum waterfall rate for maximum ruins. So calculate the mass at pinch, the mass at pinch over pinch concentration. So mass at pinch is 9 at 9 kilogram per hour over 100 ppm. We do some unit conversion here from kg to ton, and you get 90 ton per hour. Yes. So that is the minimum mass water. Oh, okay. This is example. Oh, so exercise. 1, 5 now. Yeah, you should try this. What you need to do? You draw this first. 10.29, limiting water profile. Then you create the combine limiting water profile. Draw this tangent to get the picture. About 15 minutes it is. Start it out. Because the operation here they already was it, sorted in the same order, ascending order. Maybe disgusting. So, any question? You can also ask in the chat as well. So your task is to do this exercise for 15 minutes. You can give me like one 20. So the chat. So, continue. Sure. Okay. The class. Your answer. So how to do it? I don't have the answer. But see, just a draft can be done. Mm, alright. So we start with 0 to 50, 50, 500, okay. 25, 50 to 50, okay. Let's see. What's 25, 25, we have 50, we have 250, okay. 500. Okay, so it starts with 0 to 4. Then we have 4 here, and 14 is a cumulative. 64 plus 1 is 72. Alright. Oh, you cannot draw. Okay. Alright. Oh, okay. Yeah. We start from 0 to 50. 0, ah, 0 to 50. From 0 to 4 kilogram per hour. Then we have 10, 10 to 25. So 25, 50 10, 10. 10 maybe. 5 to 15. Yeah. What else? 14, 14 to 64. 14 to 64. Oh, sorry, 50 to 64. 50 to 64, 50 around here. 50 to 500. The last one is 8. Let's see. 0 to 2, 2 to 7, 7 to 37. So this one should be 4 to 14. 450, 58. 250 to 500. Yeah, this is the limiting water profile. Then you need to combine it. 1, 2, 3. 1, 2, 3, 4. Okay. Then just open color. And another one. Something like this. This is the combined limiting water profile. The next task is to draw the region. So the pinch is at 14. 14. So 14 minimum water platform maximum use. So meaning you need to divide 14 with
Hmm, how many ppm? 14 divided by 14 kg per hour divided by 50 ppm. Hmm, 14,000 divided by 50 ppm. 280. So the minimum butter flow rate, the maximum use is, yeah, boleh tak? Yeah, yes. 14,000 after, what is it? Unit changes. Divided by 50. So we get 280 per hour. Uh, this is the pinch. 15, 50. So, any issue? Okay. So that is limiting composite curve. Why you need to learn this? Whenever you want to do optimization for the how much water that we can save, then you need to do this step now. Okay, to see. Show you another slide. What for the water cascade lah. Oops. Wow. We and this one is water efficiencies for an urban system. This is a case study. Slide number 2. Don't know. New slide 2. Yeah. Mm, this is what the casket. It's modern LV 6. Yes, and this paper. Modern paper 6. Alright. Okay. So what topic Francisco and urban system? A case study on the Sultan Ismail was at the University of Technology Malaysia. Paper is there. I have a lot of method. Oh, just model paper. Yeah. Wait, you go through first. Wait a bit.
Alright. Change that. So what the page analysis? Referring to the paper as well can. So this paper describe how the water cascade analysis. So far you have learned about sink source diagram, sink source allocation diagram, limiting composite curve, and work allocation diagram, which is derivative of sink source diagram by diagram in 2003. This is another method. This is the easiest, because you just need to calculate. You need to draw. Okay. Based on pinch analysis concept was adapted to establish the minimum water target for the Sultan Ismail Mus at the city of Indonesia. So this mosque is at the center of UTM. It's next to their library, convocation hall, and chancellery building. It's on the hill. The WCA stands for Water Cascade Analysis. Is a numerical alternative to the graphical water targeting technique known as water surplus diagram. So graphical water targeting technique is referring to the limiting conversion curve and the sink source diagram. Yes. Two cases, I'm reading the abstract first. The result compare with the saving predicted via a conventional water management solution. The conventional system predicted reduction of 25% fresh water and 19.8% generation of wastewater. Here we see what does the comprises of, where does its source missing. The WCA technique predicted saving of 65% wastewater and 51.5 wastewater with reduced only, and up to 85% wastewater and 67% wastewater with reduced in regeneration. The WCA technique based on fish analysis concept can rapidly yield accurate minimum water target in point location and water allocation target for an urban water network. So the urban sector contribute a significant percentage of water consumption, particularly in developed countries of warmer climates. In Malaysia, for example, the domestic sector contribute 60.1% of the total water consumption compared to the other sector. This is based on the injection. The majority work on urban water conservation is focusing on design of water saving gadget and wastewater recycling. In a water distribution system, it is possible to determine the maximum water recycle flow rate through appropriate water cascading. Water cascading refers to the water cascade analysis. The first key step toward minimizing freshwater consumption and wastewater generation is to establish the baseline or minimum water consumption target prior to the design or retrofit of an urban water network through the notion of water targeting. As far, okay, description of how the water cascade analysis technique was adapted to establish the minimum water target for the Sultan Ismail Mus at the city to Indonesia. The end. So the fresh water is stored in 4 interconnected distribution tanks, each with volume of 237 liters. The typical logic solution has two steps. Okay. The estimated total water fresh water consumption for most is 11,550 meter cube per year. It's a lot. During the semester, the amount of water consumed for ablution is about 16 meter cube per day on Fridays, but only 25 meter cube per day on other days. Because this mosque is three-story mosque, yeah. It's big mosque. In order to estimate a reasonable typical water saving for the mosque, daily water consumption calculation will based on normal semester days. So that is the scope of this work. So fresh water coming from the municipal water, 29 part per day. Then 0.03 ton per day goes to the kitchen, sink and sauce. So after the kitchen concentration decrease to 536 ppm. Next, some 39.07 goes to this interconnected tank, four interconnected distribution tank, each with 227 meter cube. So this water is fresh water, 0 ppm. So from there, distributed to admission, 25 ton per day. Admission, this one is for the wash machine, shower, wash cleaning, and so on. The rainwater, they store the rainwater. It's 11.4 ton per day, over 10 concentration of 10 ppm. The ocean water and water were to be filtered for solid particle like gas to conduct before going through the series treatment using automated carbon and metal filtration processes to restrict from here. So in this case, the ablution is 23 ppm concentration. Wash machine shower, so only one stream to be considered for reuse. So for this treatment, it will reduce the concentration to 4.2 ppm. So meaning you can reduce the freshwater up to uh, 21.83 instead of 29.1. How much? It's not 7.27. So you can save around 7.27 ton per day. This is done by IWERN, which is Institute of Environmental and Water Resource Management, UTM. So what they do is they propose to reuse the emission water and rainwater for the entire MOS, because rainwater is not that, how to say, stable. It's very according to availability. So the emission water, no matter what to be filtered or solid, actually. So this incoming water goes into the interconnected tank. It is being diluted to 1.05 ppm. So during the rainy season, because it's based on the availability of the rainwater, if the rainwater is enough, can manage 7.27 ton per day. So they just divert the emission to the sewer, not to be reused. This is based on page 56 of the paper. So this design allowed an estimate freshwater saving up to 25% with a payback period for investment of about 10 years. That's a long time. So the payback period, how do you calculate it? The amount net, the total investment divided by net annual saving. When we calculate, it's payback period is about 10 years. The most statistically speaking, a batch process, since all the water usability occurs in discrete time period. However, in this case, it is possible to use the WCA technique to develop for a continuous process to establish minimum freshwater consumption and wastewater generation targets. The ability of soil matrix pattern of water utilization allow the most capacity to be modeled as a repeated batch approaches a continuous system. First, a total building review is carried out to have a good understanding of the initial water plumbing and sanitation of the building. Next, data acquisition. And a station are conducted by surveying the water flow rate and contamination at the source and at the discharge. With this data, the process program of the initial water network can be obtained. Subsequently, WCA is constructed to achieve the true minimum target for the network. Finally, a new water network time before the economic basis carried out to show the total saving of the new water network. So this is the method to setting the minimum water target. So for the water cascade analysis, refer to page 58 of the paper. The main objective of the WCA is to establish minimum water target, the overall fresh water requirement and wastewater generation for a process after looking at the possibility of using the available water sources within the process to meet water demand. The first step in the WCA is to set up the table water balance. Table 6. Table 6. Okay. To determine the net water source or water demand at each purity level. So for this case, water demand we have 8, water source we have 6. Water demand is equal to sing. Okay. So so the first column of table 6, column number 1, contain the contaminant concentration level C, ascending order. So ascending order from lowest to highest. Arranged in ascending order, each oxygen level is expressed in terms of the water purity E in the second column. With the concentration of pure water set at 1 million ppm, the fraction of pure water in the contaminated stream or the water purity can be expressed as P equal to 1 million minus C over 1 million. Where C is the contaminant concentration in ppm. Start from 0. This is the first interval. So from 0, we should go to each column. So to calculate P, you use this equation, 1 million minus C. C refer to this first column. So the concentration refer to this concentration. So the third demand for each of the places is about 0 and 10. How they know? That one is based on okay. The data for water demand in table 1, the one table 1 is adapted from US EPA standard of water use. Table 3 is page 58, which stated the data for water source is in table 2, based on the data by table 4, page 58 as well, in the paper, and table 5. Yeah. It's based on BOD. Sweden, BOD concentration. That's on the SPA. So domestic water cycling BOD must be 10. There are many standard, but they use US PA. The one is BOD bro. BOD from King Abdullah Boss. So yeah, BOD is around 23. Then what else? Yeah, there's a lot of what's it? Um, data. Data. How they choose it, they didn't really explain. Let's see. CSBE. 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 21. Yeah, okay. These people evaluation that was facing the water and using the water were of similar quality. To change ppm. Many Kautsky collected on typical political position was the water in Eastern Europe. The BOT force when water was used so that responsibility to show the USPA. Okay. One is for the table one bit, how they get the 10 ppm. Oh, but the rest, they didn't. It's me. All right. Okay. If they didn't explain meaning, they do the other system safe. Huh? Okay, okay, column two now. The number of priority interval delta P equal number of water demand and the number of water source minus any duplicate priority NDP. So N. Priority interval. ND plus NS minus NDP. Then we have a delta P, number of priority interval N. So how many number? This number, they get it from the um, equation 2. This equation 2. But actually, no need to calculate. It's actually between these two concentration. There will be one interval. Uh, Application of equation 2 to the most case study yield 6 purity level. So yeah. Next, the water purity different delta P, column number 3 here. Interpreted as the difference between purity level of interval K and K plus 1. So this interval minus this interval. Yeah. But do not let's see, subtract column 1, column 2. So 1 minus 0.99999 is equal to 0.1000001 and so on. What else? Column, okay. Column 4 and 5, this is water cascade analysis. There will be no drawing, but you need to calculate. No graph though. Yeah. Control 4 and 5 contain the total flow rate for the water demand FD and the water source. So this is water demand, this is water source. At their corresponding purity level, the of water demand is fixed as negative. So this is negative. And the water source is positive. This flow rate are summed up at each purity level to give the net interval water flow rate column 6. So D plus S, demand plus source, plus represent the net water source, and minus is the net water demand in column 7. So negative become demand, positive is the source. All right. So you see here how they get this number. This 0.03 is coming from here at at concentration 0 ppm, 0.03. For concentration 10 ppm BOD, you need to sum up all of this because it's representing one concentration. So total up 29.07 negative. Oh, but this so zero doesn't so for the water source there is no BOD zero, of course. How come with zero? It's water that have been used. Even the rainwater, but 10 ppm BOD. So leave it blank. So minus 0.03 plus blank is equal to 0.03. How about 10 ppm? 10 ppm is 14 here. 25.17, this is for 23. It's we have two 23 ppm. So we need to not multiply. We need to add it. And so on, based on each consideration, just register the rate. So the next key step in the WCA is to establish the freshwater and the next step is to establish the freshwater and wastewater target for the process. In doing so, it is important to consider both the water flow rate balance and the concentration driving force suitability so that the true minimum water targets can be obtained. The flow rate balance using water cascade degrees is the water cascade, which include in the term in figure 7 to get the cumulative net water source slash demand for process. FC, this one FC. So first we assume no fresh water. So no fresh water. So for the first one, negative 0.02, negative is negative 0.03. Then you have 17.96. 17.93, sorry, and add up 17.96 and 17.96 last 5.17 goes to 721 and so on until at the end you get fresh, what is it, FWW. This is for wastewater generated. It's around 7.67 ton per hour. Next is the pure water cascade. This is the whole legend from A cascade, then we go to pure water cascade, then interval fresh water demand. So for the so oh, for the water cascade diagram in 7A, the fresh water flow rate FFW is 0 is assumed, where the net water demand of 0.03 at the first minute level is extended, which the term cascading, like a ladder down. This is based on the table 6, giving a relative of negative 1736. This currently demand only net water source down to the next property level to yield a positive wastewater flow rate. Okay, this FW is a wastewater flow rate of 7.67 ton per day. Day. At the lowest purity level of the cascade, not the cascade template. So the true minimum target can only be realized by also taking into account the pure water surplus or deficit, which is a product of the cumulative net water source demand FC and the pretty different delta P across two purity levels. So product of the cumulative the source demand and the purity different delta P here is something missing. It should be -3 times 10 to the power of -7 instead of 0. Because how we calculate? Oh, let's see. It's 0.0000. So here we do the correction. This one is incorrect. It should be 9, 10. So how we get this? Here, this one multiplied by this one. Yeah. So you get take 0.37 This is husband. Then we get, okay, step here, guys. So what else? So 0.00013 delta P times negative 17.96 times per day, you get 0.0000233. You see here? Uh, minus this with 3 times 10 to the power of negative 7. You get negative 2.23. Yeah. 0.0000234 instead of 233 because we have the half here. So you calculate this D first, pure water surplus deficit. How? The product of multiplication of cumulative net water source demand FC with the priority difference across two priority level. This one delta P. Oh, it's 220 already. Okay. Can we continue first? We can finish. So once you calculated this, then we need to do the cascading again. So this cascading is for the pure water cascade. Oh. The water surplus plus, the water surplus plus sign, this means that water is available with purity higher than what it is required in this region. On the other hand, pure water deficit minus means that water of high purity was available is required. So next is the cascading the pure water surplus deficit down the purity interval in the pure water cascade that represent the cumulative amount of pure water surplus distribution. This one, this column. Oh, okay. Do something here. Alright. So we get this. Next is what is that? Notice that for the pure water cascade in figure 7b, cumulative pure water deficit observed from second to third quality. So negative sign means is for two quality level P2 and P3 deficit on the pure water cascade which correspond to the negative region of Harare. Surplus diagram figure 9a indicate that the pure water cascade is infeasible because of the negatives plus. One is different method. It's completed here. So this deficit means there is insufficient fresh water in the network They are the result of assuming, because we assume a zero first. Huh? See here, we assume zero, no fresh water. During the water cascading, thus additional fresh water should be supplied to remove all the pure water deposit and yield a visible pure water cascade. So next is so fresh or pure water is to be supplied at the highest purity level. Highest purity level means at P equal to 0 ppm or or less. But normally it's 10 or 0 ppm fresh water. Luminous fresh water is necessary to determine the minimum flow rate of fresh water or the interval fresh water demand that will satisfy the total water demand at each purity level. The interval fresh water demand restore a feasible pure water cascade throughout the network. One is figure 7C. It shows that the interval freshwater demand FFWK is sign of each purity level K is obtained by dividing the cumulative pure supply visit by the purity difference between the freshwater supply and purity level PK of interest of so FWK equal to cumulative pure water supply visit is column over PFW minus PK. So PFW is the purity of the fresh water, which is 1. This is cleanest one is 1, meaning 0 ppm. This is a purity. Then minus the PK. PK means the next, the P2, P3 before it's cascading. For example, negative 3 times 10 to the power negative 7 is 1 over 1 minus 0.999 here. You get negative 0.03 ton per day. And for the second one, you calculate by negative 0.0000234 divide by 1 minus 0.99997. You get this big. And do the same for the next. And you get the column C, interval fresh water demand. Referring to figure 7C, a negative value for FFW means there is insufficient fresh water, whereas positive FFW means there is an excess fresh water at the purity level K. Mm, yeah. It's okay. All right. In order to ensure that there is this is a feasible water gasket which have a pinch. So from that pinch, we choose the highest negative to become the freshwater feed FFWA. So so in order to ensure there is a sufficient freshwater at all points in the network, a freshwater flow rate FFW is exactly the same relative as the absolute value of the largest FFWK should be supplied at the highest purity level of a feasible water gasket. Figure 10, the FFW4 of negative 1016 is found at the purity level P3 of the cumulative freshwater gasket. It's considered as the largest FFWK. Yeah, so this largest value goes here, then you need to do the calculation again, cascading again. So how? 10 minus 0.03, you get 10.13 minus negative 17, get 7.8 plus 25, 17, and so on. Then delta P times 10, you get this value, negative P, delta P 0.00013 multiplied by negative 7.8, get this value. So this value need to be cascading again. So here is just, okay. Then goes here, then you get the pinch 0. So this is above pinch, this is below pinch. Not that feasible with cascade. Page 63. Not that through the WCA, we have obtained the utility target ahead of design, are able to verify whether the proposed design achieved the maximum recovery objective for the plant. The water cascade, pure surplus cascade diagram can be integrated with the double water balance table to form the water cascade table WCT table 7. So once we identify this, refer back to table 6, we amend it. So instead, starting from here 0, we have another row here for the fresh water 10.16 ton per day. How you get this number? Based on this cascade calculation. This is the water cascade table. So for the water cascade table, you need to do again. You see here. Oh, 10.16 minus 10.3, 10.13 plus minus this 78 and 10.13. This one is pure water surplus TED is the is it the multiplication of delta P here. We don't have delta P, but you have it here. 1013 times 0.01 is equal to 0.0000101. This is the casting. Can you get the pinch? As you do it, so the amount of wastewater now is around 17.83. increasing because we introduce fresh water. So now the water cascade is visible. There's no negative in to take pure water supply. Meaning the water is enough. Uh, so to through the WCT, the WCA technique offer two key advantages of the water supply survey in realizing the minimum water target. The first key advantage is that the WCT clearly display both minimum freshwater FFW and wastewater fluid FWW target in the predictive net water source slash demand column. See, for example, table 7, noted in the case of no water supply station, only the minimum fresh water target is known. However, the value of the minimum wastewater flow rate target is not available from the diagram. The second key advantage of using WCT is that it's enable a designer clearly to identify the pinch causing strip and the exact water division for the region above and below the pinch to achieve the minimum water target during the network design. Referring to table 7, a zero cumulative pure water plus activity level of 0.99977 here, referring to the pinch, represent the pinch point. Notice that the pinch causing stream which exists at the level is the water source with a total flow rate of 35.17 PED. It's here, 23. You see here, 23 ppm is the pinch point here. The source, vision and wash machine, basic, stream 2 and 3. Referring to table 2, distributed from the two sources are vision S2 and wash basin S3. You know the exact stream that become the pinch. So meaning any return back to the three rule how to create the water network. So any point above the pinch must not be supplied to the any point sink or source below the pinch. It's the rule number 1. That's all. Poly. In order to realize the pinch point and to achieve the maximum water recovery objective, a portion of the pinch causing source stream, in this case the ablution has to be relocated to a process above the pinch, while the rest process below the pinch within the road design. Referring to the collective state of the source FC, yeah, out of 25.17 ton per day water source from ablution and wash machine, 708 ton per day of water found between P2 and P3 must be sent to the region. 7.8 ton of water found between P2 and P3. P2 and P3 as we send to the region above the pinch, the tips are sending water across driving force. Okay. On the other hand, 17.37 is one of water found between P3 and P4 must be sent to the region below the pinch. Okay. So, oh my God. Because this paper is comprehensive. It's also include what the regeneration. Let's say we treated some water from below the pinch, which can be reused above the pinch. The one after this. Hmm. Possible scope for process changes to reduce the water target further enhance water consumption include water regeneration and equipment modification. This is it. Water regeneration involves the partial or total upgrading uh, of water purity using purification techniques such as wastewater treatment, like microfiltration, greenhouse filter, sand filter with beads, multimedia filter, and biofilter. The regenerated water can either be reused in other water using processes or recycled to the same process to reduce further water consumption and wastewater generation. To increase water availability, finally propose the use of water composite curve and the pinch purity to guide the regeneration of water source as follows. Okay, this is the rule by Halali. Regeneration for the regeneration above the pinch. If we generate 7.8 here, it is 7.8. Water source in the region above are partially treated or upgrade its purity. Regeneration across the pinch. Water source in the region below the pinch are partially treated to achieve purity higher than the pinch purity. So meaning 17.37 we regenerated it more than 23 ppm. Sorry, less than 23. Regeneration below the pinch water source in the region below the pinch are partially treated completely. However, the resulting water source is still maintained below the pinch. So meaning, let's say uh, we treated 17.21 at 216, we regenerated, but not up to this because the pinch point is at 23. So meaning even after the regeneration, the concentration is still more than above the 23. The table 7 shows the pinch concentration of the most polluted at 33 ppm. One possible solution of soluting water source is to treat the evolution water to a position above the pinch. Evolution water refer to S2 because S2 stream number 2 is a lot. Last machine is only 0.14 ton per day. Ablution is about 25 ton per day at 23 ppm. The amount of ablution to be treated depends on the cost of the treatment equipment and analysis of the relationship between treatment equipment costs. Knowledge must be established to know the amount of water data to be treated that has an appropriate payback period. Total amount of ocean water to be treated using local filtration is set to 2.7 ton per day based on the IEWRM UTM case study. So from table 9 from the WCT show the new pinch purity at 0.9977 and the freshwater and the wastewater flow rate reduced to 4.22 and 11.89 tons per day respectively. Why? Because we treated the water. See that 7.27. So we treated the 725.25.3. 35.03 minus so 17.76. 17.1. Yeah. 25.1. Let's say 17.9. Yeah. 17.9. So we treated the 25.17 for S2 and S3 mission plasma wash machine. That one is under 23 ppm. Uh, but the treated is only 727 based on the capability of the microfiltration. How they know? They refer to this case study by IWRM. How about the photo PPM? Mm, was the 3 PPM referred? This is based on paper. This paper by Manan 2006. Yeah, this okay. After the treatment by the microfiltration, instead of 23 ppm, it can be reduced up to 4.2 ppm, which is why we have another set of concentration here, 4.2, referring to this 7.27 source. There's no demand, of course. Yeah. We need to recalculate once you introduce, let's see, once you introduce this 7.27 with 4.2, you need to recalculate back starting from zero here, fresh water, meaning you need to do it like this. Yeah, do it like this. Starting from zero, calculate, do the cascading, see where does the interval have the highest negative. So in this case, is it the highest negative is at negative 4.22 here, on here at the pinch. Put it back here, recalculate again, do the cascading, then you get the pinch shifted to level 3 and 4. Okay. So designing a water network that reuse water is needed to the shortage of fresh water and using cost of wastewater treatment. Reusing, regenerating, and regeneration and reuse wastewater reduce fresh water system and wastewater generation. Wastewater can be reused widely in the other using equation if the level of the does not interfere with the water using equation. This reduces both wastewater and fresh water volume without changing the lot of contaminant. So by doing the regeneration, we can reduce the lot of fresh water up to 4.22. Yeah, and the amount of wastewater also reduced by six times. Okay. Oh, time to do exercise, but finish this practice. The 10 minutes. The system proposed by IEWF predicted a fresh water saving of 25% and wastewater generation of 19.8%. The system suggested by the water pitch method predicted 65.1% freshwater saving and 51.5% wastewater reduction before regeneration and 85.5% freshwater and 67.7% of wastewater reduction after regeneration. So with the regeneration, both the IEWRM and the water pitch method use microfiltration treatment, hence the payback period will almost be the same, except for the additional piping system. However, the water pitch method gives much better freshwater saving. By how much the, let's see, the payback period? Mhm. What did it say? But it should be lower because the amount of freshwater saving is a lot, like 85.5% with the similar treatment. Yeah, how much? 10, 25, meaning by 4 years. Yeah, 4 years, 4 to 3 years, payback period, roughly, calculate with the regeneration. Without regeneration is 10, maybe 5 to 6 years. Mm. So this is why we do water. Sorry, not water cascade. Pinch analysis. Just to know where does where you can optimize the system. Mm. So in the worst case, there is no rainwater due to drought season. We think rainwater is a source of going through the circulation using the cascade level with partial regeneration of ablution, water, especially a percent with freshwater saving of 60.9%. Still, still better than the IEWRM. Without the rainwater, it can still save up to 64% freshwater. Well, WPA target the minimum freshwater and wastewater flow before design while the IEWRM. We need to design the system first before knowing the total freshwater and wastewater saving. That is the difference between we do the WPA, water pitch analysis, and the IEWM method, which they design the system, then they know how much. Instead of know how much you can save, then you do the design. With WPA, one can efficiently and systematically plan water saving per building, and all are able to identify a career design option priorly. Knowing the target and the maximum potential saving effect of design is indeed crucial to determine the best possible design that can be the most efficient work. Without this design target, the designer is unaware of the potential saving until the result of the work is constructed. Okay. Discuss this together. Let's see. So, uh, thank you. Attendance. Attendance first. We resume tomorrow. Yeah, any question you can discuss. So far, you have learned about um, almost everything. But after this, we will focusing on the case study, meaning later we learn about the test basket analysis with one is nice as well. What they are few related is we don't have that much. But mostly it's about the casket. It's easier. So, thank you.
Thank you, Doctor.
Thank you.
Doctor, just to confirm, untuk esok hari, you will discuss about the case study, right?
Let's see. Yeah. My junior plan is gift basket.
Okay, right. Thank you so much, Doctor.
Question, Doctor. HAN.
Yeah.
Yeah, we want to ask about the HAN. Maybe Doctor can
Heat
explain.
exchanger network?
No, heat exchanger network.
Yeah, HAN, yes. Why?
Did Doctor will teach us about the heat exchanger network?
I don't think so, because that one should be covered by my colleague, actually. My
Oh,
part is, yeah, water and gas. It's either, I think Dr. Aswal about the energy, right? It's actually network.
oh, okay.
Yeah, right. Okay, if there is nothing else, we probably begin together.
Well, Doctor, thank you.
So, yeah.